this is Discrete Structures 1. Okay, so we're going to start our discussion with the week 1 topic. And we will continue until week 2. Okay? So for the week 1 topic, we're going to discuss the introduction to logic. So of course, we have discussed already about the syllabus, okay? And then even the schedule and the topics last orientation. And we are to discuss today why discrete mathematics and the basic preliminaries. So the learning objectives for today is to define the discrete mathematics, to familiarize the goals of discrete mathematics, appreciate the study of discrete mathematics, to define logic, to appreciate the importance of logic in mathematics, and of course, identify propositions. Also, we are going to study about the conversion of propositions to propositional variables. And of course, to apply logical connectives to form compound propositions. And of course, to construct and prove statements using the truth table. Okay, now why do we need to study discrete mathematics? Okay, so as we all know, we are using discrete structures to represent and manipulate data. So computer science is not all about programming. It is not all about software engineering. So computers, according to Edgar Dijkstra, so computer science is no more about computers than astronomy is about telescopes. Okay, so that is his saying. So computer science is more about problem solving. So basically, if you are a computer science student, okay, that is your major. It is important for us, it is a must for us to know how to solve problems. So meaning to say, mathematics is the very foundation enabled for us to understand the discrete structures. Okay? So again, please remember that mathematics is at the heart of problem solving. Okay? So defining a problem requires mathematical rigor. So meaning to say your analysis will depend on your mathematical logic. Okay? So use and analysis of models, data structures, algorithms requires a solid foundation of mathematics. Okay, so as we all know, mathematics is not an objective type, right? Enable for you to solve a given problem, enable for you to get the right result, you should know the formula, you should know how to analyze, and that is of course data structures and algorithm. So to justify why a particular way of solving a problem is correct or efficient, it requires analysis with a well-defined mathematical model. So again, the very foundation of analysis is for you to know or understand mathematics. So meaning to say, you cannot avoid mathematics in your life. Okay, especially if you are into programming. If you are into analysis, okay, if you are into IT, if you are into CS, you cannot avoid mathematics. This is our foundation class. This is where we will start, okay? This is where you can start to analyze and learn or understand how programming works, how the algorithm works, how the pseudocode works, okay? So again, the goals of discrete mathematics, we have 5: mathematical reasoning, combinatorial analysis, discrete structures, algorithmic thinking, and the applications and modeling. So when you say mathematical reasoning, the students must understand the mathematical reasoning in order to read, comprehend, and construct mathematical arguments. Okay? It's not more on objective type that you have to memorize the definition, okay? Memorize the enumeration type. It's not like that. You should understand, okay? You should learn to understand the mathematical arguments. So next is combinatorial analysis. So this is an important problem-solving skill. Okay, this is the ability to count or enumerate objects. Okay, Next is the discrete structure. So basically, discrete structure is a part of discrete mathematics. That's why we are discussing discrete mathematics as a whole. Okay? So a course in discrete mathematics should teach students how to work with discrete structures, which are the abstract mathematical structures used to represent discrete objects and relationships between these objects. Okay? Next is the algorithmic thinking. So certain classes of problems are solved by specification of an algorithm. So meaning to say, if you we're talking about algorithm, we're trying to do what? A step-by-step procedure, okay? So after an algorithm has been described, a computer program can be constructed implementing it. Okay? So of course, in able for you to do a program, you should know how the algorithm works. That's how you do a program class. You don't just type your codes, okay? You should know what is the algorithm, what is the step-by-step instruction that you are going to input in your code or in your program. Okay? And the last one is the applications and modeling. So discrete mathematics has applications to almost every conceivable area of study. There are many applications to computer science and data networking, as well as applications to such diverse areas as chemistry, biology, linguistics, geography, business, and the internet. So again, class, don't forget, these are the goals of discrete mathematics, okay? That's why we need to study discrete mathematics. Okay, next, this is the reason for studying discrete mathematics. Number one, again, you have to develop your mathematical maturity. Okay, this is the ability to understand and create mathematical arguments. Second, it provides the mathematical foundation for many computer science courses, okay, including data structure, algorithm, database theory, automata theory, formal language, compiler theory, computer security, and operating system. So again, class, don't forget that mathematics is the very foundation of computer science. That's why I had mentioned a while ago that you cannot avoid mathematics. It's because this will be the foundation how you can do very well in your programming. Okay? Okay, introduction to logic. We will study, we have the PL or the propositional logic. We also have the FOL or the order logic. And then we also have the fuzzy logic. Okay? Now, when you say logic, this is the study of the logic relationships between objects. And it forms the basis of all mathematical reasoning and all automated reasoning. Now, what is the importance of a logic? Okay, so the rules of logic specify the meaning of mathematical statements. Okay, so logic is the basis of all mathematical reasoning and of all automated reasoning. So it has practical applications to the design of computing machine, okay, to the specification of system, to artificial intelligence, to computer programming, to programming language, and to other areas of computer science, as well as to many other fields of study. As we all know, class, computer is built by means of what? It started with the calculator, if you can remember. It all started with a simple computation built with the logic before we had the computer. Okay? That's why we need to study the mathematics. That's why we need to study the logic, because if you don't understand and if you don't study those basic courses, then of course, how can you do your complex programming? And how will you understand what you are doing? Okay? So next, arguments, premises, conclusion. So when you say argument, okay, it also occurs in a logic. This is a group of propositions or statements, which is divided into one or more premises and one and only one conclusion. Okay? The statement being supported is the conclusion of the argument, and the statement that support it are the premises of the argument. So later on, you are going to apply this argument, premises, and conclusion in the proposition class. Okay? So again, there are three different types of logic. We have the propositional, we have the first order predicate logic, and we have the fuzzy logic. But in terms of your course requirement, we are only focused on the propositional logic that is under your syllabus. Okay, let's start with the propositional logic, or sometimes called as the propositional calculus or sentential logic. Okay, so the objects are called proposition. When you say proposition, this is a statement, so either true or false, but not the same or but not both. Okay, so we denote proposition by letters P, Q, R, and S. Okay, don't forget about that. So the denotion, to denote a proposition, we are using P, Q, R, and S. Okay, so the basis for propositional logic are the three laws of Aristotelian logic. So we have three: the law of identity, the law of excluded middle, and the law of non-contradiction. So law of identity, a thing is itself. Law of excluded middle, a statement is either true or false, but not both. Okay? And then law of non-contradiction, no statement is both true and false. So please remember the three laws of Aristotelian logic: the law of identity, the law of excluded middle, and the law of non-contradiction. Okay. So the value of proposition is called the truth value. It's either denoted by true or false, or 1 or 0. Let me use my highlighter. So again, the truth value, I can use this one, the true or false, or I can use this one. So 1 is for true, and then 0 is for false. So either it's both acceptable. Okay. So opinions, interrogative, and imperative are not propositions. Okay, so this is a sample of the truth table. Okay, so if you are to apply the 0 or 1, 0 is for false, 1 is for true. Okay, so this is a proposition example. So the following are propositions. So today is Monday, the grass is wet, it is raining. So the statement below are not proposition. So for example, C++ is the best language. It is an opinion. Okay? It is not a fact. Okay? It is someone's opinion. Next, when is the pretest? So this one is an interrogative. So mostly if you encountered question format, okay, that is an interrogative. Okay? So do your homework. When you say do your homework, okay, it is imperative, meaning to say it is necessary that you must do. Okay, so again, so be careful. You should know how to distinguish what is a proposition, what is opinion, what is interrogative, and what is imperative. Okay. So for example, okay, so another example for proposition: 1 plus 5 is equals to 6. The earth revolves around the sun. 10 minus 4 is equals to 5, and pigs can fly. So let's check one by one. 1 plus 5 is equals to 6. Is this true? I think so. So the earth revolves around the sun. Is that true? Yes, of course. What about 10 minus 4? 10 minus 4 is equals to 5. Is this true? I don't think so. So it is false. What about the last one? Can pigs fly? Pigs can fly? Is that possible? So of course, it is false. So meaning to say, propositions 1 and 2 are true, and whereas 3 and 4 are false. Another example of proposition. So x plus 3 is equals to 5, x plus y is equals to z. When is your birthday? Pass your assignment. So sentences 1 and 2 are not proposition because they are neither true nor false. Why? Because we don't know the exact value of x, right? Next, sentences 1 and 2 are not proposition because they are not declarative sentences. Okay? What about when is your birthday? What kind of statement is this one? What about pass your assignment? What kind of statement is this one? The third and the fourth one. We have what? We have the interrogative, and when is your birthday is the interrogative, and then pass your assignment, that is imperative. Okay, let's move to the next slide. So propositional variable. This is a name that represents the proposition. So example, so again, we are using P, Q, R, S for denoting a proposition. Remember? So P, the earth revolves around the sun. Q, pigs can fly. And then R, 1 plus 5 is equals to 6. So again, that is called as the propositional variables. Okay, now we are to discuss the compound proposition. So it can be obtained by negating a proposition or combining two or more propositions using the logical connectives. So for the logical connectives, we have 6 class. We have the negation, we have the conjunction, we have the disjunction, we have the exclusive or, we have the implication, and we have the biconditional. The only basic logical connectives are, we have the negation, conjunction, disjunction, implication, and biconditional. So again, these are the basic logical connectives. So when you say negation, it means not. When you say conjunction, it means and. When you say disjunction, it means or. Okay, and when you say exclusive or, it means XOR. Okay, and then next is implication, it means if then. And then for the biconditional, it means if and only if. Okay, so not is used to not, or the negation, it is used to modify the proposition, while the and, or, if then, and if and only if are used for joining proposition. So remember that, class. So again, not is only used to modify, while and, or, if then, and then if and only if are used for joining propositions. Okay? So precedence rules. So in forming sentences, we put grouping symbols. You can use the parentheses, the brackets, or the braces. So without the presence of grouping symbol, we will assume that the grouping will follow precedence rules for logical connectives. So remember, these are the basic logical connectives. We have the not, the and, the or, the if then, and the if and only if. So logical connectives. So of course, if there is a meaning for the logical connectives, we are using symbol as well. So for the negation, we can use the symbol or the exclamation point. Okay? For the and or logical conjunction, it can be denoted by this symbol. Okay, for the and. And then for the or logical disjunction, we use this symbol. For the XOR or the exclusive OR, we are using this symbol class. So for the implication, okay, we use this symbol, this arrow, or this one. Either of the two, so this is acceptable. And then the biconditional is denoted by this symbol or this one. Okay? So please remember the given symbols for the logical connectives. Okay? because we are going to use this later on. So to summarize class, okay, the Boolean the some popular Boolean operators. So again, so we have the negation operator here. So the nickname is not. So by the way, negation operator arity is unary, meaning to say single or one component only. And then this one is the symbol for the negation or not. So for the conjunction operator, again, we are using the and. And this is the binary, the arity is is binary, meaning to say two or more. If you remember, if we are using conjunction, disjunction, implication, biconditional, we are trying to what? To join the propositions. Okay? That's why it is binary. So this is the symbol for conjunction. And then for the OR, again, it is also binary and we are using this symbol. For the exclusive OR, we are using the nickname XOR. Okay, this is also binary and we are using this symbol. Okay, and then for the implication, so implication means if, then, or implies. And of course, this is also a binary and we are using the symbol of this one, the directional arrow that is going to the right. Okay? For the biconditional operator, the nickname for the biconditional is if. Okay? And then it is a binary and we are using a bidirectional arrow. Okay? Okay, so logical connective, let's discuss it one by one. We're going to start with the negation. So again, negation is unary. Okay? So when you see the symbol, it means not. So it transforms a proposition into its logical negation. So example, so if P is equals to I have brown hair, so not P, it is not the case that I have brown hair or I do not have brown hair. Okay? So let's check. So assuming that this is the given truth table, so by the way, on the left side of the table, it is the what you call the operand column. Okay? While on the right side of the table, this is the result column. So that's the part of the truth table. You have the operand column and you have the result column. So assuming that the values, the truth values for P is true or false, okay, true and false. So not P, meaning to say we are going to get the opposite value. So of course, so true, the first truth value is true. What is not true? False, right? So next we have false, not P. What is the opposite of false? True. That's how we get these results. Okay? So again, not P is the negation of a proposition P. It is also a proposition. So for example, today is not Monday. It is not the case that today is Monday. So again, so from the previous slide, we used the true or false. I just want to show you that we can also use the 0 and 1. So remember, what is the value 0? It indicates what? It indicates false. What about 1? It means what? It means true. So of course, again, so not P. What is the opposite of 0? That is 1. And the next is 1. What is the opposite of 1? That is 0. Okay, so that is the truth table for negation. Either you use the true or false or the 0 or 1. Okay? So just a sample proposition here for the negation and not. Okay? So, for example, class, the sun is shining. So, of course, what is the negation of the sun is shining? The sun is not shining because we use the not. Okay? Next, for the proposition Q, the program is running, and of course, the not Q or the negation of Q is the program is not running. Next, another example. So we have R here for the proposition. The value of X is positive. So the negation of R or not R, the value of X is not positive. So again, for the negation, we always use the word not. Okay? Okay, moving to the next slide. So after the negation or the not, the next logical connective is the logical and or the conjunction. Okay, so when you say conjunction, we are using this symbol. And of course, we are using the word and. So of course, the logical and is used to combine two propositions to form a logical conjunction. So for example, okay, for example, my first proposition is I will have salad for lunch. So that is P. So I have a second proposition, which is letter Q. I will have steak for dinner. Now, I want you to form the logical and I want you to use this symbol, okay? P, okay, P and Q or P logical and or P conjunction of Q. So, to join the two proposition, I will write the first statement of P. I will have salad for lunch. And again, what is my conjunction? The word and. So next, I will write the statement, the proposition statement of Q. I will have steak for dinner. Now, I have what? Logical conjunction, which is I will have salad for lunch and I will have steak for dinner. Okay? So that's how you form the logical conjunction using the and. Okay? Okay, next. So now we know how to use the conjunction and, but what about the truth table? Let's try to create the truth table. Okay, so the logical, okay, the logical connective and is true only when both of the propositions are true. It is also called a conjunction. Okay, so assuming that we have these values, the PQ, okay, we have 0, 0, 1, 1, then for P, and then for the Q, we have 0, 1, 0, 1. So this is the probable inputs of the P and Q. How to get the result? If we're using the logical and, okay, let's answer one per row. Okay. So using the logical and 0 and 0, what will be the result? We will have what? We will have 0. Okay, next. What about 0 and 1? Let's talk about values. We're using 0 and 1 as of now. Okay, what's the next? Conjunction of 0 and 1. Okay, is that correct? Is that 1? We're using and. Okay, the answer is 0. What about 1 and 0? You are using and. That is, yes, that is also 0. What about 1 and 1? What is the result? Okay, very good. If you are familiar with the logic gates, I'm not sure if you're done with that subject. So it's the same with the truth tables there if you're going to compute for the logic gates. Okay, it's like that and is multiplication. Okay, it's more on how will you're going to understand in creating the truth table. It's like 0 times 0 is 0, 0 times 1 is 0, and then 1 times 0 is 0, and then 1 times 1 is 1. Okay, it's because it's n. Okay, do you understand, class? Okay, very good. Let's move to the next slide. Okay, now, as you can see here, this one, I use the true or false truth values. Okay? For the logical connective, so again, don't forget, the left side contains the operand columns and then the right side contains the result columns. Okay? So, of course, the true multiplied by true is true, true multiplied by false is false, and false multiplied by true is false, and false multiplied by false is false. It's the same with 0 and 1. Okay? So note that the conjunction P1, P2 until Pn of n propositions will have 2n rows in its truth table. It's like more on 2 raised to 2. That's why you have 4 sets here. That's why you have 4 rows. Okay? Okay? So it's the same truth table. So it's just an explanation. In logic, the word but is sometimes used instead of conjunction and and. Generally, the word but is used in place of and when the part of the sentence that follow is in some way unexpected. Okay? So therefore, if P and Q are statements, then P but Q means P and Q. Okay? So sometimes you can use the but instead of and. Okay, next. So let P is equals to mathematics is easy. And then Q, the propositional variable Q, I will pass mathematics. So therefore, the conjunction of P and Q, mathematics is easy and I will pass mathematics. So again, we combine the two propositions by only using the word and. Okay? That's why this is called as conjunction. So the proposition will only result into true if the statements P and Q are both true. If one of the statements result into false, the entire proposition will result into false. So how are you going to how are you going to use the word and in the next example? Today is Monday, the sun is shining. What is the answer? What is the answer, class? Today is Monday and the sun is shining. Okay, let's move to the next slide. So after the negation, after the end, now we are going to discuss the logical OR. So by the way, when you say logical OR, it means disjunction. And we are using the symbol. Okay, we are using this symbol, or if you want to use it in the proposition, you can use the word OR. So again, OR is also used to combine two propositions to form their logical disjunction. So conjunction is and, OR is disjunction. So example, if my propositional variable P is equals to my car has a bad engine and my propositional variable Q is equals to my car has a bad carburetor, then what is the logical disjunction of P and Q? So my car has a bad engine. As you can see, I only write the statement or the proposition from letter P. And then next, I use the word or. And then I wrote the statement Q, which is my car has a bad carburetor. So meaning is like and or in informal English. So that's how you're going to write the logical disjunction. You're just going to use the word or. So now, this is how you're going to compose the truth table for logical OR. So again, 2 raised to n. So you have two statements, which is P and Q. So we have 4. That's why we have true, true, we have true, false, we have false, true, and we have false, false. Now, note the difference from n. So again, if this is OR, if you are going to apply this if you are going to create the logic gates, how are you going to write? Or is like plus. That's my hint, okay? So for example, true plus true is equals to true. True plus false is equals to true. False plus true is equals to true, and false plus false is equals to false. Okay? So note that logical or Q means that P is true or Q is true, or both are true. So this operation is also called as the inclusive OR because it includes the possibility that both P and Q are true. Okay, so let's try to apply the 0 and 1 table. Okay, so again, the logical disjunction or logical OR is true if one or both of the propositions are true. Let me use my pen. Okay, so this is the logical end. Now, let's try to solve for the truth table for the logical OR. So 0 plus 0 is 0, right? What about the next one? What's the next row? What's the next result? That's 1. And then 1 and 0. What about the 1 and 1? What is the result? You have 1. So now, so logical OR, that is our truth table if we're going to use the 0 and 1. So 0 and 0, 0. 0 and 1 is 1, 1 and 0 is 1, and 1 is 1 and 1 is 1. So that's how you're going to compose the truth table for logical OR. Okay? So now, for the statement for the logical disjunction, just an example again. Okay? So again, we're using this symbol for the disjunction OR. So, and we use the word OR to for the logical disjunction. So for example, mathematics is easy. That's the first propositional variable P, and then the next propositional variable Q, I will pass mathematics. Now to form the logical disjunction for P and Q, so I am going to write the first proposition of P, which is mathematics is easy. Next, I am going to write the disjunction OR, and then next I am going to write the what? Propositional statement of the variable Q, which is I will pass mathematics. Therefore, okay, the logical disjunction is mathematics is easy or I will pass mathematics. Okay, so the proposition will result into true if the statements P or Q are true. If one of the statements results into true, the entire proposition will result into true. Okay, so that is disjunction OR. Okay, another example. What is the answer, class? Today is Monday. That is the propositional variable P. Q, the propositional variable, the sun is shining. So find PQ. What's the answer? Using this junction. What? Today is Monday, or the sun is shining. Okay? So that is your answer. Next, so after the negation, after the and, after the or, next we have the exclusive OR. Okay? So exclusive OR is denoted by this symbol and by the nickname of XOR. So it combines two propositions to form their logical exclusive OR. So for example, the propositional variable P, I will earn an A in this course. And then the propositional variable Q is equals to I will drop this course. Now, to form the logical exclusive OR, so I will either. Okay, this is the keyword. earn an A in this course or I will drop it. Okay? But not both. Okay? Okay. So check this out, class, this truth table for the exclusive OR. Let's check the difference between the OR, logical OR, and the exclusive OR. So as you can see here, if the truth values are both true, then it will be false. The result is false. Okay? But true and false, it will be true. False and true, it will be true. But false and false, that would be false. Okay? So note that if you're using the exclusive OR, it means that P is true or Q is true, but not both are the same. This operation is called as the exclusive OR because it excludes the possibility that both P and Q are true. Okay, that's why it is called as exclusive. Okay? Okay, let's try to apply it using the, let's try to construct the truth table using the zeros and one. Let me use my pen again. So exclusive or XOR of two proposition is true when exactly one of the propositions is true and the other one is false. Okay? So for example, so again, we have the AND here. We have the OR here. Now let's try to solve for the exclusive OR. Okay, 0 and 0, what is the result? That is 0. What about 0 and 1? That is 1. What about 1 and 0? That is 1. What about 1 and 1? That is 0. So class, please remember the only difference from the OR of exclusive OR, in case that there are two true, P and Q are true, it will be false. Okay? So remember that, class. That is exclusive OR. So an example here. So the propositional variable P is equals to mathematics is easy. The propositional variable Q is equals to I will pass mathematics. So therefore, if you are to combine these two, either mathematics is easy or I will pass mathematics. So either of the one only. So meaning to say the proposition will only result into true if one of the statements is true. So how can you form this one? Try to form the exclusive OR. So propositional variable P, today is Monday. So propositional variable Q, the sun is shining. Try to compose, class. What is the proposition? Either today is Monday or the sun is shining. Very good. Okay, now moving on to the next one, we will have the implication. Okay? So this conditional statement, either you're going to use the word imply. Okay? You can use the word implies. Okay? This one. So if you see this symbol, the directional arrow that is going to the right, you can use the word imply. So if P is true, then Q is true. But if P is not true, then Q could be either true or false. So example, the propositional variable P is equals to you study hard. And then the propositional variable Q, you will get a good grade. Okay? So P implies Q. Okay? If you study hard, then you will get a good grade. So remember, class, if you're using the implication or implies, we are using what? We are using the word if and then. Okay? Remember that. So by the way, P is equals to hypothesis or antecedent or premise. When you say Q, that is the conclusion or the consequence. So again, if you are going to use the implication or implies, you are to use the if and then. Okay, let's try to solve the truth table. As you can see here on your screen, so we have the given truth values here for the P and Q. Okay, we have 4 sets here, the true and true, the true and false, the false and true, the false and false. So again, true and true is true. So if P is true and Q is false, then that will be false. This is the only one that will be false, okay, for the implication. And then false true, that is true, and then false and false, that is true. So again, remember that in implication, the only false case is the true and false. So P implies Q is false only when P is true but Q is not true. Okay? Okay, now, let's try to solve the given truth table using the zeros and ones. 0 and 0. Okay, what's the value? Let me use my pen again. Okay? Okay, that's 1. Next, very good. 0 and 1. Let's go back to the previous slide. I think you're confused. Okay, again. What is the only one that is false? If your P is true and your Q is false. Okay, let's go back to the next slide. Okay, so what's the answer? Okay, very good. Okay, what about 1 and 0? Okay, very good class. Okay, next, 1 and 1. What is your answer? Okay, very good. So that's how you're going to compose the truth table for the implication. So remember that. So let's read this one. Okay, the implication of P implies Q can be also read as, so either you can read this as if P then Q, P implies Q, if P Q, P only if Q, Q if P, Q when P, Q whenever P, Q follows from P, P is a sufficient condition for Q, Q is a necessary condition for P. So either you can read it in this way, class, in different ways actually, all of this. So these are just an example. If you buy your air ticket in advance, it is cheaper. If x is an integer, then x squared is greater than or not equal to 0. If it rains, the grass gets wet. If the sprinklers operate, the grass gets wet. If 2 plus 2 is equals to 5, then all unicorns are pink. Okay? So again, we are using if then for the implication, and of course the symbol is the directional arrow going to the right. So remember, class, that P is equals to hypothesis and Q is equals to conclusion. Next, this is the last one, class, okay? So we have this is the 6th logical connective. This is what we call the biconditional. So again, the biconditional is denoted by the bidirectional arrow. Let me use my highlighter, class. Okay, this is the bidirectional arrow. Okay, is the proposition that is true when P and Q have the same truth values, it is false otherwise. So by the way, this symbol, this mathematical notation is equivalent to this one. Okay? This one is equivalent, okay, for the biconditional. So P implies Q, okay, and then you're going to use the and symbol here, and then Q implies P. It is equivalent. Okay? Now, let's go to this one. The logical connective biconditional, so P, the bidirectional arrow here can be equivalent or read as. So again, there are other ways to read. P if and only if Q. P is a necessary and sufficient condition for Q. If P then Q, and conversely, P if Q. Okay, that's how you're going to read the biconditional. So, for example, x is greater than 0 if and only if x squared is positive. So, the alarm goes off if a burglar breaks in. You may have pudding if you eat your meat. Okay? So, either whatever you use, that is all acceptable as long as it's within here. Okay? So, you can use the if and only if. You can use the if here. Sorry, this one. Okay? Or you can use this also. Okay, converse, inverse, contrapositive. Consider the proposition P implies Q. It's converse if the proposition Q implies P. It's inverse if the proposition is not P or implies not Q. It's contrapositive if the proposition not Q implies not P. So that is converse, that is inverse, that is contrapositive. Okay. Now, for the biconditional if and only if, so let's check the truth table here. So as you can see here, the only truth here is of course the if the both truth values are the same or true. Okay? And then if not, it is equals to false. So meaning to say, so biconditional mathematics is easy. Okay, that is the propositional variable P and Q. I will pass mathematics. So therefore, mathematics is easy if and only if I will pass mathematics. So again, we use the if and only if for the biconditional. So how are you going to form this one? Example, P, today is Monday, Q, the sun is shining. What will be the proposition of this one? Today is Monday if and only if the sun is shining. Okay. So let's try to answer the table a while ago. Okay, now, let's try to read this one. Okay, so again, we are going to work on the biconditional. Okay, 0 and 0. What will be the result? Okay, very good, because both of the truth values are the same. What about 0 and 1? Okay, very good. Next, 1 and 0. Okay, very good. What about 1 and 1? Okay, very good, class. So going to the next slide. Okay, so to summarize the truth tables, there is the summary of all of our answers. So we have the P here, the propositional variables P and Q, and we have the logical AND, we have the logical OR, we have the exclusive OR, we have the implication, and we have the biconditional. Okay? Let's try to solve about the negation of P. Let me add another one. Okay. What's the answer? 0. Okay, that is 1. Okay. Next, 0. Okay, 1. And then 1. That is 0. And then another 1, that is 0. Of course, So again, when you say negation of P, it means not P or the opposite of its value. That's why 1, 1, 0, 0. We just have to get the opposite of these values. Okay? Very good, class. Okay. So just to summarize again, so we tried to get the negation of P a while ago from the previous slide. So let's try to get the negation of Q also. So again, opposite of true is false, right? And then false is true, true is false, and false is true. So just get the opposite. Okay? Okay, next. This is what? I use the OR. Okay, so you just, for example, I want you to compute for the logical OR of not P and not Q. So to get the result of these two, get the negation first, which is this one, and then get the result. Okay? So that's why, so F and F, false and false, that is false. False and true is true, true and false is true. It's like using your addition, okay? And then true and true is true. It's like, let me use my pen again. Okay, if it's 0, let me write. Pardon with my handwriting. 0, 1, 0, I'm sorry. And then 1. Okay, let's get the result. So, of course, 0 and 0 is 0. 0 and 1 is 1. 1 and 0 is 1. And 1 and 1 is 1. Okay, that's how you're going to compute for a truth table. If, for example, I want to get I want you to get the negation first. Get the negation, then after on get the result. Okay.